talked about all the concepts, and then we can see more examples tomorrow, see more examples in our homework tonight. One thing that I think we talked about a little bit on Friday, but I think is important for you to have down in your notes, is what a rate is. Okay? A rate is a ratio. Okay? So every rate is a ratio, but every ratio is not a rate. That's important to understand. But a rate is a ratio in which units do not cancel and or cannot be converted to the same thing. The rate that you guys are probably most comfortable with or most familiar with, just give you a couple examples here, would be miles per hour. Okay. Now, when we see miles per hour, and I have students that are still struggling with this in college courses. Okay, because in my upper level courses, we worry about units as much as we worry about quantities. Okay. So when we see 60 miles per hour, we need to realize that the 60 miles is your numerator. That division is your per. Does that make sense? And then the hour is a unit of one. So 60 MPHs is that right there. 60 miles divided by 1 hour. That's the ratio that we look at. Okay? And because miles is a physical distance, and hours is a time, okay, you cannot change miles into hours or hours into miles, right? Does that make sense? Okay. So we leave it as a rate. Okay. Same thing happens with, maybe my car gets 30 miles per gallon. That means I get 30 miles of travel for every 1 gallon of gas. If I think about that, miles is a distance, gallons is a volume. You can't take one and change it into the other, so we leave them alone. You guys, I think we talked about at the end of the day, I asked if anybody had a job. If I make $12 per hour, okay, that's $12 on top for every 1 hour on the bottom. You can't change a dollar amount into an hour. Okay, those concepts are not one-to-one, right? Okay. Now, if it was like feet over a mile, like 1 mile over 5,280 feet, okay, that's a ratio because those can be converted into the same unit, right? Okay. Because they're one-to-one. They're a distance compared to a distance. Okay. If it was a currency compared to a currency, like dollars to euros, okay, then we wouldn't call it necessarily a rate, okay. But there are mathematical, and this is where we get in trouble sometimes. If you ever anybody ever had to go across seas or to a different country and have to change money, call it a currency rate or an exchange rate, okay. It's really not a rate though, okay, because it's a one-to-one. We're changing. So that language we use in kind of that arena might be contrary to how we use it in math. Okay. Why do I say that? Some of these questions are going to be kind of that structure where, if I look at this first one, some of these questions, guys, you're going to say it's pretty elementary. Okay. Some of these questions you're going to think it's pretty advanced. It's pretty high level stuff. Okay. And that's proportions can get, we make them very, very simple. We make them very, very, very hard. Okay. This one says a designated hitter made 8 hits in 10 games. 8 hits in 10 games. Find the ratio of hits to games. Okay. Well, this is going to be a rate because I can't change hits, that action, into the action of a game. Does that make sense? Okay. So I leave it as hits over games when I'm done. Okay. So hits over games. Okay, so I had 8 hits for every 10 games, right? What's that reduced to? They both have a 2 in them. So even though I get 8 hits for every 10 games, what we usually do is say, well, that means you got 4 hits for every 5 games. Okay, and if you watch baseball or anything like that, or sports in general, it's inundated with ratios, batting averages, okay? Yards per catch, yards per game, those types of things for quarterbacks and receivers and running backs, that kind of stuff. They are rates, yards per catch. Yards up top, catches on the bottom, divide them out, right? Okay. Batting averages, hits per plate appearances, per times I go to the batter's box, okay? And what they do with that stuff, and so we change it all into numbers, and then that allows general managers, okay, it allows coaches and managers themselves to make decisions about those players, right? I'm gonna pay Garrett Cole $1 million for every start that he makes for the Yankees. I better make sure that this guy's going to give me some outs, right? Okay, that he's produced data that says that he's worth $1 million for every time he goes out on the mound. Okay. What I want you guys to understand, though, is if this player only plays 10 games, is that really a good prediction for his next 10 games or his next 20 games or his next 40 games? Okay, probably not, right? Okay, if you've watched baseball at all, like Major League Baseball, does anybody know how many games during the Major League Baseball season? 162. Okay, every year. So baseball player, if you're not familiar with Major League Baseball, batters get anywhere from like 4 to 5 plate appearances. They go to the bat 4 to 5 times every game. Every year, throughout all of Major League Baseball, on opening day, it's inevitable somebody will go and hit 3 home runs. Okay? We'll get 3 home runs. And then SportsCenter will come on and say, this person is on pace to hit 400 some odd home runs, 3 times 162. They're going to say they're going to hit 3 home runs in every single game. Is that kind of misleading? Right? Yeah? Okay. But if they play, let's say, 90 games, okay, and that person has, let's say 80 games, just make 81 games, let's say halfway through the season, that person has hit 6 home runs. Okay, SportsCenter can probably make the argument. They've shown enough that says we can argue that they'll hit around 12 home runs for the year. That kind of makes sense? Okay, so if you have, that's called a sample space. If you have a large enough sample space of at-bats or of games, you can use that information to make predictions then. Okay. Now, what's nice about that is some people make predictions off of like a track record. Okay, Garrett Cole has been a very good, if you don't know him, he's a major league pitcher. He's made very good career stats for the last, 5-6 years. Okay, so the Yankees say, yeah, we'll pay him $300 million over the next 10 years or whatever. Okay, some players have had like one breakout season, and then a team will say, okay, well, they've shown that they have the capacity to be awesome. We'll give them $200 million, and then they suck for the rest of their career. Okay, so there's still risk involved, but if I'm a person making those decisions, I want to have data for it. And that's what math is about. Now you guys always ask, well, how can I use this in real life? We learn the mathematical concepts so that we can allow them to help us make decisions, okay, for future things. Okay. Now, are they the best decision? Maybe, maybe not. But I'd rather make a decision over something with some support rather than just making a decision flying from the seat of my pants. Does that kind of make sense? Okay. So that's what we use a lot of our math for. Be careful when you see spouse to reduce. Next one, be careful on the wording. Okay, because a lot of people just say, I get in the habit of just taking the two numbers and comparing them. So there are 60 or 76 boys in a sophomore class out of 165 students. Find the ratio of boys to girls. Number one wrong answer would be what? Or what do you think the number one wrong answer here is? A lot of people write 76 to 165. What did I just compare? Boys to the whole class. Boys to students, right? What do they want? They want boys to girls, right? So I'm going to go boys to girls. That's 76 boys. Girls is found by taking the total number of students minus the 76 boys, right? Is everybody okay with that idea? So that would be girls, whatever that difference becomes. And then that would be your ratio. Just be very cautious of how they phrase things. And of course, exam's going to do that, because and especially if maybe you get to I don't know how many questions on the course exam are multiple choice, but like ACT, they give a ratio question like this. One of your options will be 76 or 165, and that'll probably be option A, because just the way your eyes focus on your solutions, giving us see that right away. Oh, that's the answer. Those are the numbers that are being used. Or option B is in that difference, 76 over 165 minus 76. So just be on the lookout for those types of things. Next one, I think you can do a couple different ways. Okay. So the cable that is 42 feet long is divided into lengths in the ratio of 3 to 4. What are the two lengths? Okay. So we've got like segment 1 here and segment 2 here. And they are in a ratio of 3 to 4. Basically meaning if I take that first one that has the value of 3 with it, if I multiply it by 4, it will be the same length as if I took the one that has the 4 with it and multiplied it by an amount of 3. Okay? So essentially 4 of those segment number 1s end to end will make 3 of those segment 2s end to end. Okay? That's what this is arguing. We want that to total 42. Okay? Well, 3 plus 4 is not 42, right? Okay? So these have been reduced. Okay? Get rid of that. 3 to 4 could have been 6 to 8, right? Does that make sense? Does that still reduce 3 to 4? The 3 to 4 added to 7. 6 to 8 adds to 14. But what if it was 9 to 12? That gives me 21, right? And maybe right there you can get the idea of how we're going to get these two segments. If I double 21, does that give me 42? So what if I doubled 9 and doubled 12? Does that add to 42? Is 18 over 24, does that reduce? They both have a 6 in them, right? Does that reduce 18 reduce to 3 if I divide 6 out? Does 24 reduce to 4 if I divide 6 out? Okay? That's kind of a trial and error technique. I don't know if that's the best route. It works. Okay? But if you remember the question we did the other day with the extended ratios about the triangle, this one here, it's the same thing. It's just not a triangle anymore. It's just a segment addition problem. Can I take the 3 and the 4 and say that the 3 has been reduced by some amount, so let's unreduce it by multiplying by x. Let's unreduce the 4 by multiplying by x. If I add those together, it should give me the entire length of the segment. 7x equals 42? Does x equal 6? Okay. Well, then if I multiply that by 6, multiply that 3 by 6, does it give me my 18? And multiply the 4 by 6, does it give me my 24? So that's one way. Okay. I don't know if anybody would really recognize or use this technique. There is a question in your homework that you have to do this with eventually. Let's say that I've got, would you guys agree that the side length or the, like that distance right there is 3 out of, so this one was 3, this bottom one they said was 4. Would you agree that this 3 is out of a total of 7? If I look at those two, does that kind of make sense? Okay. Well, how does that 3 then compare to if I enlarged everything an amount out of 42? Does that make sense, everybody? If I cross multiply, I get 7x equals 3 times 42. When I do proportion, you're going to see me do this a lot. And whether you do it or not, it's up to you. But I think it's stupid for me to multiply 3 and 42, because I know my next step is going to be to undo some of that multiplication through some division by 7, right? So I don't ever multiply those things together, because I know that if I take this and divide by 7, divide that by 7, will those two things divide? So it gives me x equals 3 times 6, which is 18. Does that make sense? So that tells me that this 3 here, out of the 7, 3 out of 7 compared to the 18 out of 42. So 18 out of 42, 18 is that smaller distance, right? And then define, if I have an 18 out of 42, then the remaining would be 42 minus 18, which would be 24. Okay. So a lot of different ways of doing that style of problem. We'll come back to some more story problems. And like I said, the story problems, they can get as simple as, hits per game, that question. And they can be then, I'll show you one tomorrow that is pretty confusing. All right. Removing context. So as you do your story problems, I'm going to give you a handful tonight for homework. As you do them, you might generate this. So I just want to make sure that we understand how to solve these types of proportions. Okay. We talked on Friday that if you have a proportion, you're going to take that amount there, and you're going to multiply by that amount there, right? Those were, if you remember, those were called the means. We take the product of the means. I'm going to make this a capital B, because my B's look like my 6's sometimes. So when I do those, I get that. And now I'm going to multiply my extremes, which would be those two. I'm going to write that as 6 and B plus 1. I'm deliberate about my, at least when I'm demonstrating this with you guys, I'm going to be deliberate about how I write this. I didn't do any multiplication there, right? I just implied what I'm going to multiply by. Because I want to remember, I want to see in my work the algebra that reminds me what I need to do with this 5. Multiply by that B, right? And then I'll multiply by that negative 1. So I need to remind myself that I'm distributing here. And then I'll do the same thing. 6 times B, and then 6 times 1. When people make errors with this, they will write it as they'll go like 5B minus 1. They'll forget to distribute to the negative 1. Or they'll write 6B plus 1 and just forget to distribute to the positive 1. So just be on the lookout for that distributive property and doing that correctly. Now if I'm going to subtract 5B from both sides. So 1B, I'll subtract 6 from both sides equals negative 11, right? My hopes are that we do enough of these to kind of prove to you how easy they are to check. If I plug negative 11 in right here, I'm going to get negative 10, right? When I plug negative 11 in right there, I get negative 12, right? Does that equal 5, 6? Okay, and if you've done it correctly, that will always be a yes. Okay? Otherwise, you're wrong. Okay? Now, some people last class said, well, yeah, because the negative divided by negative is a positive, and I divide the 10 and the 12 by 2, I get 5 over 6, right? I can reduce that 1 on the left to turn it into the 1 on the right. What I think might be easier is to multiply those two numbers. What's the product of those two numbers? Negative 60, right? What's the product of those two numbers? Negative 60? Because those products are the same, you know that your answer for B is correct. No other number for B will give cross products to be the same value. Is it okay? All right, now what stinks, and there's no avoiding it, is when we have binomials in that either extremes position to one another or the means position, or they could be in both. Okay, here we've only got it in the extremes. But let's kind of talk about what happens here. If I'm going to cross multiply, and this is going to be one of the harder versions of this problem. You don't see a whole lot of these in your homework. See a couple. I get that, right? I'm going to cross multiply. And when I multiply these, we get -4. Okay? Questions like these very well could be on the end of course exam. And this is my argument of why I think Algebra 2 should come before geometry. You saw some of this stuff last year. You dealt with some of this, but it was for a very kind of small part of algebra. Algebra 2 focuses on this a great deal. And you would be much more successful in this demonstration, this discussion that we're going to have. Probably wouldn't have to be had if we took Algebra 2 first. Okay? But there are other reasons why we take geometry first. When I see this, I have to, that's foiling, right? You got a binomial times a binomial. So you need to do first times first. So what's 3x times x? When you multiply like bases, you add the exponents, right? So 3x times x is 3x squared. Okay? So that's first times first. Outside times outside will be 3x times that 2. So it gives me 6x. Then inside times inside will be -1 times x. And then last times last will be -2. And it gives me -4. Okay? Something I want you guys to know or remember. Obviously you learn, everybody's heard the phrase FOIL, right? Okay, but when I see that in the foiling technique, all it means to me is distribute several times. Distribute the 3x to everything in the right set of parentheses, and then distribute the -1 to everything in the right set of parentheses. And that's what the FOIL is. Does that make sense? Okay. Now, does anybody remember what we do when we have a power of 2 as your highest power? Exponents greater than 1, you want to think about factoring. And when I think factoring, I need my equation equal to 0. Okay? So we're going to take this thing and rewrite it so that -4 is a 0. So if I want to make that a 0, do I have to add 4 here? Add 4 there? So now I get 3x squared plus 5x plus 2 is equal to 0. Okay. Now, last year, and I'm going to show you where you can find these resources. Let's see here. Come to the website, scroll down to where it says, or gives you this yellow table with the blue table inside it. Over here where it says factoring, you click on that. It's going to give you some remedial videos here of factoring. First one is the ones we like the most. It says factoring when the coefficient of A is 1. That's not what we have here. We have A coefficient is not 1, so it's going to be this middle column of videos. Or we could use this last column of videos. Okay? This is all stuff that was introduced to you. You learned it last year. You demonstrated somewhat of a proficiency with it last year. We just don't have the time this year to relearn that in class. Does that make sense? I want to open your eyes to it because you're going to see this stuff pop up all the way through the rest of your high school career. Okay? Algebra 1 comes first for a reason, because as we move through other problems throughout sophomore, junior, senior year, intermediate steps might generate a quadratic equation like this. And we have to be able to address that. We can't just shut down and quit because we don't remember how to do this. First thing we talked about last year is we want this number, we want that number, if possible, to be a 1, right? So the first thing we're going to try is to see if all of these coefficients and constants are divisible by it. And in this case, they're not, right? So the next thing you do, you guys remember hearing the phrase AC method? You're going to take this as your A term, that's your C term, and you're going to multiply them together. So 3 times 2 equals 6, right? Okay. Now, once you get that 6, you're going to be looking for 2 numbers that add to give you your B term, but multiply together to give me that 6. Okay? So what 2 numbers multiply together to give me 6, but add up to give me 5? 3 and 2. Okay? Now, in this case, it was the same 3 and 2 that I multiplied together to begin with, right? That won't always be the case. Okay? I got to look at the factors of 6. That will add to give me 5. Now what we're going to do is we're going to rewrite our equation so that it is 3x squared plus, now instead of writing this 5x, we're going to write that 5x as a combination of those two. We'll write it as 3x plus 2x. And then our plus 2 that was already there. So that whole process is called the AC method, gets us to rewrite our 5x, our B term, as a sum of 2 other terms. Does that make sense? Is 3x plus 2x still 5x? We've just expanded it, right? We've pulled it apart conveniently, okay? Some people think that they can just do that, 5x. Well, I can make that 1x and 4x. You can, but it's not going to allow the next steps to happen. Okay? Some people say, I can make it 2.5x and 2.5x. You can, but it's not going to make the next steps happen. And the next steps are to do this. You're going to group the first 2 terms, and then you're going to group the back 2 terms. And now we're going to look for a GCF, a greatest common factor, that is in the first 2 terms. What will divide both these things in the green parentheses here? Do they both have 3x in common? When I divide 3x squared by 3x, leaves you with just x, right? When you divide 3x by 3x, it leaves you with just 1. What will divide the back 2? 2. Dividing 2x by 2, you get x. Dividing 2 by 2, you get 1, right? You guys remember that when you did this, whatever was in that set of parentheses, if they were identical, then x plus 1 became a factor. That group that was in the parentheses. Do you remember what the other factors end up being? It's everything else. It's the 3x plus 2 that were on the outside of what I colored green there. So, that thing right there and that thing right there are the same. They do the exact same thing. But one of them is written as a sum and the other one's written as a product. Does that make sense? The one on the bottom right, if I want to make sure the x plus 1 times 3x plus 2 equals 0 is the same thing as 3x squared plus 5x plus 2. Excuse me, I'm losing my voice. You can, for us, what's x times 3x? 3x squared, right? What's x times 2? 2x. What's 1 times 3x? 3x, right? So you got 2x and 3x, isn't that 5x? And now 1 times 2, last times last, gives me that plus 2. So this thing I've got here in the bottom right is accurate. Now here's my question. If I've got two numbers that multiply together to give me 0, what does one or both those numbers have to be themselves? 5 times what equals 0? 0. So x plus 1 times what will give me 0? What do I need x plus 1 to be multiplied by so I get 0? 0, right? What do I need to take 3x plus 2 and multiply it by so that I get that to be 0? 3x plus 2 times 0 gives me 0, right? So because I'm multiplying two numbers together and I'm getting a product of 0, that means either the x plus 1, that factor right there, has to be 0. Because if that's 0, then I get 0 times 3x plus 2, which has got to be 0. Or 3x plus 2 has to equal 0, because then this thing is 0 times x plus 1. Isn't 0 times x plus 1 give me 0? Do you remember doing that last year? Taking those two little factors and setting them equal to 0? And then you can solve these. X is negative 1, and x is negative 2/3. And those then end up being my two answers for this proportion. Okay? Now, here's the thing. The geometry is trying to target cross products. Can I cross multiply to get an equation I'm able to solve? Sometimes that equation's linear, very easy to solve, like that b plus 1 over b plus 5 or whatever equals 5, 6. That wasn't too bad to solve, linear. Here, cross multiply, same geometry, much more difficult algebra, right? Okay. If you remember from last year, there is a fail-proof way of factoring. And this is what I would suggest to you on the end of course exam if you forget, where you don't see how to factor it. You guys remember seeing that x is equal to the opposite of b plus or minus b squared minus 4ac over 2a? Quadratic formula. Do we know what a is in this case? B, and that's C. So now if I just substitute B squared would be 25. I get that. Now I just got to evaluate. And this is where people make mistakes on these and they don't like the quadratic formula. The square root is a set of parentheses. The square root is a grouping term. So you have to do this first. You have to look at that stuff there and do your order of operations in there first. Order of operations in there says do the multiplication first. Do 4 times 3, which is 12, times 2, which is 24, right? And rewrite that now as 25 minus 24. 25 minus 24 turns into 1. 2 times 3 on the bottom gives me 6, right? What's the square root of 1? Just 1, right? So what this does gives me these two answers. X could be negative 5 plus 1 over 6, or negative 5 minus 1 over 6. Negative 5 plus 1 is negative 4, and that reduces to negative 2/3. Negative 5 minus 1 is negative 6, and that reduces to negative 1. Are those the exact same two answers that we found over there factoring using the AC method? The only hang-up with this type of stuff is the thing that I highlighted, which we call it the discriminant. If you're on the end of course exam, know that you're going to have this calculator. And if I struggle with the discriminant, I can go square root, type in b squared minus 4. A was 3, C was 2. You see how it gives me my 1 right away? Okay. I like this because I can actually make that B, make that A, make that C, and then come down here and say, well, B, make it 5, A, make it, what was it, 3, C, make it 2, and then you see right here it's evaluating and making that total 1 then. It does that algebra for us. Does that make sense? But that's the number one place that people make a mistake on that process. Okay. When we work with proportions, there's 3 properties that we want to keep in mind. Now, I'm going to teach these so that you can, if you are a person that wants to memorize them, you can. But the idea of algebra is that we should essentially not have to memorize things. If we know the property that generates these 3, that's the math that I want us to know. Okay? Essentially, these properties say in that first one, if I look at the proportion on the left and compare it to the proportion on the right after it says is equivalent to, all they've done to the proportion on the left to get the proportion on the right is they looked at reciprocals. They took both fractions and flipped them upside down, right? Okay? Now, what I want you to know is that is only true because of what we know about cross-multiplying. Okay? If you start with A over B equals C over D, if you cross-multiply those, does that give you A times D? That make sense? If I cross-multiply those, does it give me B times C? And when we cross-multiply, we say that we want those products to be equal, right? That was the idea. Okay? Well, let's see if the proportion looks any different if I go B over A equals D over C. Okay? So that blue one is talking about this. We took just the reciprocal of the proportion. If I cross-multiply these blue ones there, what's that product? A times D, right? If I cross-multiply there, what's that product? B times C, right? Is this product here, that set of cross products, identical to that set? We got the same thing, right? So that proves to us that if I work with, like, say, 2/3 equals 4/6. You guys all agree that's true? Then this is saying, well, 3/2 must equal 6/4. Do I get 12 equals 12 right there? Is this 12 still equal to that 12? That makes sense, everybody? So the reason why you're allowed to take the reciprocal is because cross products are still equivalent statements when we're done. Okay? This one here, all they're doing is they're going to take those two things there and they just switch spots. They interchange them. Okay? Now think about this. So those are, you guys remember those being called the means, right? So you're going to hear me say that it is legal, it is allowable for you to exchange your means. You're allowed to exchange the means. So if I say, now it gives us different proportions, different ratios. So let's say 2/3 equals 4/6. That's true, right? If I replace these, I get 2/4 equals 3/6. Two separate, different fractions than what I started with, right? But is the proportion still true? Is 2/4 the same thing as 3/6? They're both 0.5, right? Okay? And the logic there is if I take that cross product, I get AD. Take that cross product, I get BC. Over here, cross product AD, cross product CB, which is the same thing because of the commuter property as BC. All right? You're going to want to, at some point, take a proportion and adjust it or manipulate it. And you're going to ask yourself, is this legal? Is this allowable? And all you got to do is check to see if the proportion you started with, if those cross products are equivalent to the cross products of the manipulated version. Okay? If they are, then what you did was allowable. Here, what they're doing, and we'll be done after this one, what they're doing here is that they're going to take and basically add whatever the denominator is to the numerator. So let's say I have 2/3. We know 2/3 is equivalent to 4/6, right? So they're saying that is equivalent to 2 plus 3 over 3. Just add that denominator to the numerator. Should be the same as 4 plus 6 over 6. And now you can add those together and say, okay, well, 5/3 is equal to 10/6, right? Does that make sense? But I want to answer why. I want to talk about why does this work. Can I take, so this is like a common denominator. That 3 on the bottom is the common denominator, right? I can separate that to 2/3 plus 3/3, can I? If I started with this, would you most commonly write it as 2 plus 3 over 3? Same thing over here. You'd write this as 4/6 plus 6 over 6. You would most commonly write it as that. And usually we look at two fractions and merge them with a common denominator. Here is knowing that common denominator and separating it. But what is 3 over 3? Isn't it 1? What's 6 over 6? Isn't it 1? Did I start with an equation? Was that an equation? If you add the same thing to both sides of an equation, is it still balanced? And here all we did was add a 1 to both sides, right? Okay. So that's kind of maybe the specific way of doing this, but we can look at cross products again. If I cross multiply those, I get D times A plus B. Cross multiply those, I get B, C plus D. This says to distribute, right? So I get DA plus DB, or BD, I don't want to write it. Here I get BC plus BD again. What do you notice about that BD and that BD? They're the same, right? So don't they cancel out? I'm left with just DA equals BC. Is that the same thing I get right there when I cross multiply? DA, BC. That makes sense? So my hope is that you don't memorize those individually, because there's 3 properties there, that the reciprocals of a proportion are still equivalent. Okay? The interchanging of the means in a proportion still produces an equivalent proportion. And really the interchanging of the extremes is true as well. That works. Okay? And in here, if you can add the denominator to the numerator of both ratios in your proportion, still get a true proportion. I don't want you to memorize those in 3 or 4 separate properties. What I want you to know is that when you cross multiply a manipulated proportion, if your cross product is identical to the cross product of what you started with, then what you did was okay. Okay? If it's not the same, then that is not a property of proportions. Okay? There's a lot of things we can do with proportions to manipulate them to create equivalent proportions. And there's 1 or 2 things that you can't do that will create proportions that are not equivalent. Okay? So I just want to make sure that you understand you can't just do anything haphazardly that you want to. But there are a lot of things that we can do that generate equivalent proportions. And those approaches, these properties right here, are going to allow us to know what the sine, cosine, and tangent buttons do on our calculator. Okay, it's kind of the foundation trying to be laid for getting to those things. Okay. I sent you guys an email that had some story problems in it. It has some just already set up proportions that you have to cross multiply. Read the email because it tells you things that I want you to do on that worksheet. You don't have to do them all. There's a handful that I tell you to kick out. Tomorrow in class, I want to talk about that first thing, answer any questions or confusion that we might have on it, and then that will be due tomorrow evening in Math Excel. Okay? So make sure you get started on it tonight. Come in tomorrow, go over a handful of those, and then I want to pick up, there's a couple questions at the end of this that I want to, some real hard, I think, proportions towards the bottom end of this that are pretty difficult. And you see some applications of where this stuff's used, like biology and stuff like that. And that should be in your email now.